Micro-meteoroids, small particles of rock and metal floating in space, present a significant hazard to spacecraft and space stations orbiting Earth. Despite their minuscule size, often no larger than a grain of sand, these spacefaring pebbles can cause substantial damage due to the high velocities at which they travel, typically tens of kilometers per second when encountering Earth's orbit. The impact of micro-meteoroids on spacecraft and space stations has profound implications for mission safety, design, and operation, necessitating advanced protective measures and continuous monitoring to mitigate potential risks. The kinetic energy possessed by micro-meteoroids, a result of their high speeds, can lead to severe punctures or abrasions on the surface of spacecraft and space stations. For context, a micro-meteoroid traveling at 10 km per second has a kinetic energy equivalent to its mass in TNT exploding upon impact. This can compromise the integrity of the outer hull, damage critical systems, or even penetrate pressurized modules, posing a direct threat to the safety of astronauts on board space stations like the International Space Station, ISS. One of the most notable incidents highlighting the danger posed by micro-meteoroids occurred in 2016 when a tiny particle created a 7 mm chip in one of the ISS's windows. While the station's windows are designed to withstand such impacts, the incident underscored the potential for more severe damage. In response to these threats, spacecraft and space stations employ various protective strategies. The ISS, for example, utilizes Whipple shields, a type of spaced armor consisting of multiple layers of different materials. When a micrometeoroid strikes the outer layer, it disintegrates, spreading its energy across a wider area before reaching the subsequent layers. This significantly reduces the impact force, protecting the station's main hull. Advanced materials and design strategies also play a crucial role in mitigating the impact of micrometeoroids. Researchers continuously explore new materials with high tensile strength and resistance to penetration, such as Kevlar or Nextel, which can be used in the outer layers of spacecraft. Additionally, the orientation and design of spacecraft components are considered to minimize exposure to micrometeoroid impacts, protecting vital systems and extending the operational lifespan of satellites and other space vehicles. The impact of micrometeoroids also has implications for the longevity and reliability of spacecraft. Over time, the cumulative effect of numerous impacts can degrade the surface materials of spacecraft, impairing their functionality or leading to the failure of onboard instruments and systems. This degradation necessitates the development of materials and coatings that can self-heal or resist the erosive effects of micrometeoroid impacts, ensuring the continued performance of critical mission components. Monitoring and predicting micrometeoroid activity is another essential aspect of protecting space assets. Space agencies around the world, including NASA and the European Space Agency, ESA, maintain extensive catalogues of known debris and micrometeoroids and use sophisticated models to predict their paths and potential collision risks with satellites and space stations. These models inform collision avoidance maneuvers and mission planning, reducing the likelihood of catastrophic impacts. Furthermore, the study of micrometeoroids provides valuable scientific insights into the composition and dynamics of our solar system. Samples collected from spacecraft surfaces or through dedicated missions, like Japan's Hayabusa missions and NASA's OSIRIS-REx, offer clues about the early solar system and the processes that led to the formation of planets and other celestial bodies. In conclusion, micrometeoroids pose a significant threat to spacecraft and space stations, necessitating advanced protective measures, materials, and designs to mitigate their impact. The continuous effort to understand and defend against these tiny but potent hazards underscores the challenges of operating in the harsh environment of space. As space exploration advances and humanity's presence in space grows, addressing the threats posed by micrometeoroids will remain a critical component of mission planning and spacecraft design, ensuring the safety and success of future endeavors beyond Earth's atmosphere.